Thank you very much, Kevin, for the nice introduction, and thank you all for joining me here this morning for our live demo on Uncle. My name is Andre. I'm product manager here in Unchained, dealing with this instrument. We at Unchained are all about combining different things in one instrument. In that vein, Uncle will combine fluorescence, static light scattering, and dynamic light scattering to give you all the tools you need to characterize your proteins for their stability. Because we have everything packed in one machine, we save you bench space, we save you training time, you need to interact with only one instrument, and that makes your life easy. Uncle also focuses all these three measurement modalities on only 9 microliters of sample. You can run between 1 and 48 samples, and you don't need very much to characterize very early on in the stage of clone selection, for example, which one you want to focus on further. For our fluorescence measurements, we use 2 different laser systems to excite fluorescence, and we measure full spectrum fluorescence. That way you as the user are in full control of your experiment. You can focus on the protein intrinsic fluorescence if you prefer, or you can use a reporter dye. In the demo today, we'll look at 2 experiments, a readout of intrinsic fluorescence and also a readout of SYPRO Orange. For the static light scattering, we also use those same 2 lasers and look at how is the static light scattering signal changing in the temperature ramp, for example. And because static light scattering is a measure of molar mass, this will give us information about how our sample aggregates in, for example, a thermal ramp or an isothermal experiment. So fluorescence for unfolding of proteins, static light scattering for the aggregation of proteins. We have DLS in the instrument as well, which gives us an orthogonal measurement of aggregation. It looks at the hydrodynamic size. So we have both static light scattering with molar mass for aggregation and dynamic light scattering with the actual size. In the demo, we will look at 2 analytes, a monoclonal antibody and RNase A, and we'll look at their profiles in a temperature ramp looking at the intrinsic fluorescence of the protein itself and also at SYPRO Orange. I will first show you how to load the samples in the uni and how to insert the uni into Uncle, then how to set up the experiment in our software, and then in the end, we'll look at the data that we've collected and see what conclusions we can draw about those 2 samples. Before doing anything with the software, let's take a look first at how we introduce the sample in our sample holder called the uni. Let's go to the other table where I can show you in a little bit more closely focused in on the system what it looks like. Give me 1 second while I glove up. So our uni is sold, is provided in these plastic tubes to keep it clean and keep the dust away from it. It's an anodized black aluminum frame with 16 quartz cuvettes. Each of these cuvettes has a volume of 9 microliters, and you can put 1, 2, or 3 into Uncle, so between 1 and 48 samples at a time. Volume in each of these cuvettes is 9 microliters, and in order to load it, we will use this loading tool. As you can notice, it clicks into place. There's magnets in there that make sure that the uni is positioned right under those loading tool helper lines, if you want. In order to load it, take a single channel pipetter. I have my sample here in this case, sample number 1. I aspirate 9 microliters. And then I move down this helper line to the entrance of the uni cuvette and inject my sample. Let me do that again, the next one. The pitch of the individual wells in the uni is the same as in a 384 well plate. So you can also use a 16-channel multi-channel pipetter. So the capillary force actually wicks the sample into the cuvette, and it's really easy to load. I'm only going to do 2 now to save some time. In order to prepare this uni to be loaded into Uncle, we will use this blue frame. The frame, as you can see, has a silicone gasket that looks something like this. And we provide you with 2 fresh gaskets for every uni. So every time you run a new fresh gasket, you don't have to worry about any contamination between experiments. I have already prepared this uni frame here with 2 gaskets. In order to grab the uni out of the loading tool, you take it in the tool like this, close it, close the little metal lock, and then your uni is ready for an experiment. Before showing you how to put this into Uncle, let's go take a look at the software and how to set up the experiment. let me share my screen. When you launch Uncle software, we have two softwares. We have an analysis software and we have a client software. The client software is the software that controls the instrument. This is the first screen that you're seeing after you've logged in. And if you click applications, you have the whole range of a dozen different applications you can use. We're going to be using the TM-TAG with optional DLS today to look at the intrinsic fluorescence of the proteins. And for the second experiment, we would use TM using SYPRO because that is specifically tailored to using a reporter dye. Setting up the experiment is the same in both cases. So and I'll exercise it now with you for the TM-TAG with optional DLS. So I click that. We're creating a new project, our Uncle demo project. You can write freeform in here to give it a little bit more information about the run. And then next we have to select our samples. I've already prepared an Uncle live demo set here. So as you can see, we're going to be looking at IgG in a tris buffer, pH 7.4, and then at the same buffer in 50 millimolar salt added to it, and then 250 millimolar salt. We use that same buffer array for our RNase A. And here we have a schematic of the unis, and we need to populate that. So we can click our sample, click and drag it over. However, if you want to click and drag over 48 samples, it can take quite a while. So we can also highlight all of our samples here. We do a replicate of 2 and then click the first cuvette we're going to load and say replicate, and then it will automatically populate that. So now we have all of our samples set up in the first uni and set them up in duplicate. When we have populated our samples in this view, I can click finish, and that will take us to the next stage where we can set our experimental parameters. In this case, we're looking at a linear temperature gradient going from 25 degrees Celsius to 95 degrees Celsius. And we're also acquiring our DLS at the beginning, and at the end of our gradient. The DLS parameters are stated here, and the instrument will determine, or the software will determine, what the total length of your experiment is. You can change the ramp rate if you choose, if you so chose, and then you can see that the temperature or the total duration will change accordingly. When we've set this up the way we want it to, I'll click apply again, and then the software will ask me to load samples. I will unshare my screen now so you can see what it looks like to load uni. When it comes to interaction with the hardware, I have our preloaded uni here. And the samples in here are sealed. So I took my gloves off in order to work with the computer. Because the samples are sealed, you don't have to worry about evaporation. You also don't have to worry about contamination of your sample. Everything is safely in here, and the silicone gaskets close the cuvettes at both ends. When the door is open, we'll take this tray light cover off, and then we place the uni on the uni tray. You could hear it clicks in place because the same magnets we use to hold the uni in the loading tool are also used to position the uni here. We can put 1 or 2 or 3 here, replace our tray light cover, so here, and then I'll return to the software and tell it to close the door. Because we don't want to rush a thermal ramp, we can't fit this about 2-hour ramp into a 20-minute live demonstration. So what I've done is I've run these samples already, and we can now go ahead and review the data that I have recorded. Let me share my screen again. So now we're not looking at Uncle client software. That would be the one to control the instrument. Now we're looking at Uncle analysis software. We have the 3 uni schematic up in the upper left corner, and you can select a sample by clicking it here directly. But you can also choose your sample by clicking it here in the table. So right now we're looking at the fluorescence data here for our monoclonal antibody. Let me take this view away so I can see more. When we compare the fluorescence data for the sample in the pH 4 tris with the pH 7.4 tris with sodium chloride, we can set up an overlay like this. And what we see is that the melting temperatures don't change much. I haven't showed you this yet. Let me add the drop lines for the melting temperature. The software determines the melting temperature by looking at the first derivative of the fluorescence plot. And the fluorescence we're looking at here is BCM, the barycentric mean. That is the wavelength that separates the area under the curve in two equal halves. That way we can use Uncle's full spectrum fluorescence, or we can fully capitalize on Uncle's full spectrum fluorescence and integrate a signal of 120 wavelengths and look at a very low noise, high signal data set this way. However, if you prefer to analyze by area, by ratio, or by peak height, you're free to do that as well. It's only the click of a button. Now, when we're comparing these melting curves, we're looking at the inflection points. That's where the melting happens. We see that between the salt-free buffer and the buffer with 50 millimolar salt, we have almost the same melting temperature. It's actually, looking at the table here, we have 70.4 and 70.2 degrees Celsius. The melting temperature for the 250 millimolar salt condition is a little bit lower. It's about 1 degree lower. We do also simultaneously to fluorescence record our static light scattering signal, which is our readout of aggregation. Adding that in the software like this, we have a second y-axis now on the right side that has our static light scattering signal at 266 nanometers. That's the UV laser that we're using. Looking at the aggregation behavior, we see a little bit of a more varied picture compared with what we saw for the melting temperatures. Now we see that the 50 millimolar salt condition aggregates first. We have intermediate behavior for the high salt condition, and the salt-free sample actually has the latest aggregation. It seems to be the least aggregation prone. We can also here in this case add drop lines for the aggregation very easily, and that mirrors again what I just said. The 50 millimolar salt has the lowest aggregation. The tris buffer without salt has the highest one. I did mention earlier that we don't only have one static light scattering detection in here, but two. So let me add the second one in here. So we have in the dots here, now we have the signal from the 266 nanometer laser, the UV laser. And we also have the second data set here for the blue laser, the 473 nanometer laser. You can see that the same trend that was apparent for the short laser is also visible here in the blue laser. So 250 millimolar salt aggregates first, and the one in tris alone without salt aggregates last. But you can see that this peak is later. Static light scattering is a function of wavelengths, and the shorter wavelength laser has the higher sensitivity and will pick up on aggregation first. Static light scattering actually decreases with a fourth power of the wavelengths. That's why we can use our 266 nanometer laser as a very sensitive readout, and we use the 473 nanometer laser, which is less sensitive, to be able to give us a wider dynamic range of our measurement. So we can get both of these data sets are recorded simultaneously, and we have a very sensitive aggregation detection, at the same time a very broad dynamic range for it. We also did record, of course, dynamic light scattering simultaneously before and after the ramp. And if we look at that, for our sample here, our monoclonal antibody in the tris buffer, we see a distribution of radii centered around, distribution of diameters centered around 10 nanometers. That is pre-ramp at 15 degrees. And after our ramp is finished, we see an increase in the size to above 1 micrometer. So let me show you the overlay of the two. The sample started before the ramp at around 10 nanometers in diameter, and it's more than a micrometer after the ramp. So a clear aggregation, and the DLS confirms orthogonally what we saw from our static light scattering before. When we look at the other experiment I ran, that would be the experiment with SYPRO Orange. SYPRO Orange is a reporter dye that, as a protein unfolds, it will bind to hydrophobic patches that are being exposed, and it changes its fluorescence. So we're looking at an increase in the fluorescence signal from SYPRO Orange, and that will tell us about the unfolding of the sample as well. Here is the fluorescence plot. That is, now we're looking at area here for our monoclonal antibody in the salt-free condition. And if we look at the melting temperatures that the software determines, we now see 2 melting temperatures. Before, in the intrinsic experiment, we only saw 1. When I'm adding our static light scattering signal here, it becomes pretty apparent that the second increase in the fluorescence of our SYPRO Orange is due to the aggregation. So having access to both the fluorescence data and the static light scattering data lets us differentiate between unfolding and an aggregation event that in SYPRO Orange looks like it's a second unfolding event, but in fact, this change in signal is due to the sample aggregating here in this case. What I also want to point out is that the first melting temperature we're determining here is about 3 degrees lower than what we saw earlier in the intrinsic experiment. So SYPRO Orange, by virtue of interacting with the protein, can destabilize it, and that's what we're seeing here. So for our sample, for our IgG sample, because it has strong intrinsic fluorescence, the SYPRO Orange experiment is not ideal because it shows slightly lower stability values, and also the second event that we're seeing here is due to the aggregation, which the dye can't differentiate between. This is the part looking at the monoclonal antibody. Let me go back to our intrinsic data set and then just take a look at the tris at the RNase A. So for the RNase A, we see this kind of curve, which doesn't really show any melting behavior. We see a change in the BCM wavelengths in the range of about 2.5 nanometers, but we don't really see any melting behavior, which is not surprising if you think of that's the fact that this is RNase A, which is low in aromatic amino acid residues. It in fact doesn't have any tryptophan at all. So we would not expect, looking at the sequence, to see much of an unfolding signal from our intrinsic fluorescence here in this case. It's interesting to look at the aggregation because we also do not see any aggregation. The static light scattering signal, if anything, decreases a little bit. It does definitely not increase. So our intrinsic signal for our RNase A sample is not ideal. However, looking at the SYPRO Orange trace, let me show you this. We see nicely overlaying melting curves for the salt-free, the salt-containing, low salt, and the high salt condition, and the 3 melting curves also overlap really nicely. So in this case, different from the monoclonal antibody before, because this analyte does not have any, has a very low amount of aromatic amino acids in it, we need the help of the dye to find out about the melting behavior. UNCLE, again, gives you full flexibility with 2 excitation wavelengths for your fluorescence, full spectrum readout, and also flexibility when it comes to evaluating the aggregation, in this case, with the 2 wavelengths we can use here. This is summing up what I wanted to show you in terms of data interpretation or data evaluation analysis. I think I could show you that there are some samples where the intrinsic fluorescence is indicated. There are some samples where the SYPRO Orange, the reported dye fluorescence, is indicated. And UNCLE leaves you in control to show, look at whatever characteristic of your analyte that you want to focus on. And as I said, this wraps up the data part. So let's take a look at what we have in terms of questions in the chat.
All right, Andre, thanks for that excellent presentation. I'm back here to ask you, the Q&A that have come through the webinar interface. So if anyone out there still has a question and wants to type it in, just search for that Q&A button in your Zoom navigation bar, hit it, and we'll get to as many of those as we can. All right, so first up, how long does an experiment take, and can that thermal ramp be controlled?
The total duration of the experiment depends on the number of samples and your parameters for the ramp. So I'm kind of answering both questions in one. You can set the ramp rate. The software will tell you how long the experiment takes as a consequence, and because every sample is read by itself, the ramp rate and the number of samples will govern the length of the experiment. I would say give or take about 2 hours. A little bit under 2 hours is something you can do. If you want to go to a super shallow ramp rate, of course, it will take longer, but you are, again, in control, and you can set the ramp rate and also potentially a delay between reads if you want to not overly expose your sample to the lasers.
Sure. What concentration of protein is needed for an unfolding experiment?
Concentration of the protein depends on the size of the protein. Let's say an IgG type molecule, 150 kilodaltons, normal amount of aromatic amino acid residues. I would say 0.05 milligrams per milliliter is a good lower limit. Upper limit, we've run up to 200 milligrams per milliliter, which works. Probably also beyond, but the lower limit is 0.05 milligrams per milliliter for an IgG type molecule.
Okay. And then how can UNCLE differentiate between unfolding and aggregation?
We differentiate between the 2 conformational stability and colloidal stability by integrating the signal from two readouts. We have the fluorescence readout, gives us the conformational unfolding stability, and we have the static light scattering, which gives us information about the colloidal stability, the aggregation. By looking at both of these at the same time, same sample, same temperature ramp, you get these two pieces of information simultaneously. And you as the user, by looking at the two traces relative to each other, you can differentiate, like we did with the SYPRO Orange example, what is due to unfolding, or what changes due to unfolding, what changes due to actual aggregation.
Okay. I see that you have DLS at the initial temperatures and the final temperature. What can we learn from that?
The dynamic light scattering is an orthogonal read of aggregation. So in static light scattering, very sensitive, run at the same time as our temperature ramp, we will pick up on the increase in molar mass. Dynamic light scattering looks at the hydrodynamic size, and we use that as an orthogonal readout of our aggregation. There is an application in UNCLE where you look at only the DLS in the temperature ramp. You can do that as well, and you would be able to monitor the hydrodynamic size increase as a function of temperature.
Okay. And then there's a question about buffers. Do you have any thoughts on starting buffers to recommend for an unfolding test, or perhaps maybe with the buffer we use today?
So, I mean, we started the experiment with TRIS with here pH 7.4, which is a very usual buffer. I guess most proteins like a little bit more salt. I would say start your experiment with a condition that you know your protein likes, and then try to take it a little bit and see how it reacts. So maybe go higher in salt, maybe go lower in salt, maybe try some excipients. But I think PBS is oftentimes a go-to for a first test. We're oftentimes doing PBS. This time we wanted to try something different. That's why we used TRIS this time. But start with a neutral buffer that your protein likes, and then try to stress it a little bit and see how it reacts to it.
Yeah, and I'd say definitely when you start with that kind of neutral, inoffensive buffer, you'll start to see the failure modes of your antibody too, and can design your excipient screens for those failure modes.
And what I didn't mention before is we also have colloidal stability applications in here. You can measure the diffusion interaction parameter, KD. You can measure the second virial coefficient, B22. And that way you can also predict what the behavior of a certain excipient is. So you you can guide your design of experiment that way.
Yes. So can UNCLE be used with viral vectors like AAV?
Yes, UNCLE can be used with viral vectors because viral vectors, for one thing, they are proteins. So they behave like other proteins as well. They will also unfold, they will also aggregate. An interesting thing about viral vectors like AAV is the phenomenon that they eject their genome at temperatures that are lower than the actual protein melting temperature. And because UNCLE can incorporate dyes, we have established a method using SYPRO Gold that will allow you to look at the ejection of the genome from the viral vector in a temperature gradient. I actually did a webinar on that 10 days ago, 2 weeks ago. So go to our website and you can watch it. I'm talking now in depth about how to use the viral capsid stability app for characterizing your AAV sample, also in freeze-thaw cycles. But long story short, UNCLE can also be used for AAVs and other viral vectors.
Okay. All right. And I want to thanks, Andre, for an excellent presentation on UNCLE and for answering those questions. Thank you also to the audience who joined us today live. If you'd like to reach out to us to have a deeper conversation about UNCLE or indeed any of our instruments, we'd love to connect with you. So thanks again for attending and have a nice day.
Thank you.